In the last video, I told you that today we're going to be talking about the easy system, and it's not probably going to be easy for you. Well, I hope it is. I mean, if I'm doing my job the right way, it will be easy for you. So we need to talk about what easy actually is going to stand for. So in these previous examples that we've been doing, you have noticed that sometimes we get these double bonded carbons, and these double bonded carbons will have like maybe a methyl group up here and an ethyl group down here or something like that. And I say, well, we can't use cis and trans in order to rank these or in order to look at them. And the reason is because cis and trans deal with hydrogens. And in this particular instance, to the left hand carbon, there is no hydrogen that's going to be there. So this still cannot be cis and trans. But as you can imagine, we have to devise a way in order to compare those two things, because they can be compared. They are different. The methyl group on top and the ethyl group on the bottom. So I'm not looking at hydrogens, but I'm still looking at two different groups. And that's where the easy system comes in. The easy system is used if the molecule has what we call various substituents on the main chain. So on the right-hand carbon, I could still maybe get a methyl group here and a hydrogen there. That's okay. That's okay. But by default, this is not a cis and trans. The left-handed carbon does not have a hydrogen for me to compare. So I can't use cis and trans for that reason. But I can rank them. I can rank the two groups on the left-handed carbon, and I can rank the two groups on the right-handed carbon. I'm just not comparing hydrogens anymore. So this is how we rank the groups that begin to appear. Number one, you're going to focus on the double bond. Just like you did with cis and trans. We're going to look at those carbons and we're going to see what's on them. Number two, we determine the priority of the left-handed carbon. Which one has the highest priority? Number three, we then determine the priority of the right-handed carbon. Which one of those groups would have higher priority over the other one? Number four, if those high priority groups, if the highest groups are on the same side, it is the Z notation. If the highest groups are on different sides, then this is going to be the E notation. Very similar to cis and trans. If the hydrogens were on the same side, this would be called a cis, wouldn't it? And if the hydrogens were on different sides, this would be called the trans notation, right? So this is what we would use for hydrogens, and we compare hydrogens with each other. The Z and the E form is what we would use if hydrogens are not present. That's what this boils down to. Now, as a student, I always was confused with Z and E, and this is how I remembered it. Z groups are on Z same side. You've got to sound Russian, all right? Z groups are on Z same side. So if you can remember that, Z groups are on Z same side, and say it with Z's, then you will never forget the orientation of Z and E. Z same groups are on Z same side. And you'll get it every single time. All right? So in order to see this, we need to do some examples, right? I'm all about the examples, folks. If you've not learned that yet, then, you've not been paying attention. I want to give you as many examples as possible. So let's take a double bonded carbon. There we go. And each one of these will have its legs just like before. But this time, let's put a bromine here and a hydrogen here and a chlorine here and a CH3 there. This cannot be ranked with cis and trans. The reason? Well, my left-handed carbon has a hydrogen, but my right-handed carbon does not. So in the previous examples, we would say, nope, 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 no cis, no trans, whoop, go on to the next one. That was an easy question. But now we can rank them, and we'll rank them using the Z and the E system. Now, how do we do this? Typically, we rank them by looking at the atomic number. The highest atomic number will give us the highest priority. And it's the atomic number that is directly attached. You do not add them up. Don't do that. Don't add them up. It's the number that is directly attached to that carbon. All right, so if I take a look at the atomic or the periodic table, and I take a look at the atomic number of hydrogen, hydrogen is a 1. Bromine, everything has a higher atomic number than hydrogen does, right? So bromine has a higher atomic number, that number on top in the periodic table, than the hydrogen does. So because of that, bromine is going to get the highest priority here. On the right-hand side, well, I need to compare chlorine's atomic number, and I need to compare that to only carbon's atomic number, because that's the one that's directly attached to it. Out of these two, chlorine has the highest atomic number from the periodic chart. All right, so I'll circle that one. And it looks like the highest priorities are on Z same side. So this is a Z orientation. And that's the way that I would write it in front of the name. All right, so let's see if we can name this thing, right? The longest carbon chain. Oh, the longest carbon chain here is 1, 2, 3. 3 carbons. So 3 carbons is a propene. All right, so I don't want a number here because that's not closest to my double bond. I want a number there. So there's carbon 1, there's carbon 2, here's carbon 3. So on carbon number 1, I have the ene group. On carbon number 1, I also have a bromo group. So 1 bromo. On carbon 2, I have a chloro group. So 2 chloro. And now what I do, because there's just one double bond and that's it, in the very front of this name, we normally put cis or trans without a parentheses. We normally put cis or trans. The E or Z typically does get a parentheses around it. Don't ask me why. I can't give you an answer. But this is the Z notation. So I would write Z, 1 bromo, 2 chloro, 1 propene. Woo! What a doozy, right? So let's try another one. We've got a carbon, double bonded carbon, and I got the legs. Here we go. On this side, I'll do a chlorine, and then here I'll do a CH2 with another chlorine. On the right-hand side, let's do CH with a CH3 and maybe a CH3 like that. Oh, I'm getting crafty, aren't I? And then CH2, and then OH. And now we need to compare these two. We need to name it, maybe, right? Can we name it? We'll see if we can name it. And then we'll go through and we'll figure out, is it E or Z? So let's do that first. Is this E or is this Z? That will be the easiest part to answer. So we'll do that one first. Left-hand carbon, I have a chlorine. And on the left-hand carbon, I don't include everything. I told you we only include the adjacent atom, whatever that is. And here, the next in line is a carbon. So the only thing that I'm comparing here is the chlorine on top and the carbon on the bottom. I don't care what else is after that. That is not my job. That is not the purpose of E or Z. The purpose of E or Z is to take a look at the adjacent atoms only and compare those adjacent atoms with each other. You forget about everything else if stuff is there, unless it's a tie, but you forget about everything else. So out of those two, chlorine and carbon, Chlorine is going to have the highest priority because it has the highest atomic number. So I'm going to circle that one just so I don't forget that. Notice I didn't do anything else with this chlorine out here. I mean, there's a chlorine there. I don't care that this group is bigger. That is not the name of the game. The name of the game is to compare the adjacent, the ones directly attached, and that's it, no more. The right-hand side. The right-hand side, I've got this directly attached and that directly attached. That is a tie, folks. I've got a carbon to the top. I've got a carbon to the bottom. I move on to the next one. All right, well, what is the next one? I don't really count the hydrogens. Okay, those hydrogens are not part of the main chain. To help you out with that, I could rewrite this if I wanted to. This is a CH2. So H and H, and then it goes to an OH. That is the proper way that this thing is structured. Little trick. Okay, so I go to the next atom. The next atom in line, no matter which way I go with it up here, is going to be a carbon. So now I'm comparing a carbon to something else again. And the next in line down here would be the O. Notice I'm only comparing now the next in line. Forget about everything else that came before. I'm now only simply comparing the carbon on top to the oxygen on the bottom. And the oxygen's going to win. The oxygen has a higher atomic number than the carbon does. So the CH2OH would be the highest priority group. That is how we rank the priority groups in the E and the Z nomenclature system. One at a time. One at a time. Baby steps. Baby steps. So the chlorine's on top. The CH2OH group is on the bottom. They are on opposite sides. And because they're on opposite sides, they're not on the same side. So that means that this is the E notation. Okay, now can we name this? Oh, well, I've got an OH group. We know that's an alcohol. And then here I've got this carbon and that double bonded carbon, and then I can continue on that carbon chain right there. So, we could name it. We've just not seen an example like this before. So let's go through and figure out what my longest carbon chain is. All right, so here's 1, and then it goes up here for 2. I really do want to include that double bond in there because that's part of the parent chain as well. I can handle that, not a problem. And then I need to come down, and there we go. So it looks like this is a 1, 2, 3, 4. So butane is where we would start. However, this is not an ane, it's an ene, because there's a double bond in there. Well, where does that double bond happen? From the left-hand side, that's a 1-2 position. From the right-hand side, that's a 1-2 position. But the alcohol here, it takes preference. I've not really talked about that yet, but it will. You're going to learn that. That alcohol forces this to be 1 and this to be 2. So this is going to be a 2-butene. And because we have an alcohol group, that alcohol has an ending of OL. Well, we can also squeeze that in, but now this thing is getting more complicated. So here's a time where hyphenating that name is going to do you good. So this is a but-2-ene. That way we can make sure that you understand the double bond happens at 2. And at carbon 1, we can make sure that you understand that the alcohol group is at that location. So but-2-ene 1-ol, or sometimes people would write 2-butane 1-ol. And sometimes they'll write 2-butene 1-ol. Either way you want to do it, whatever, I don't care. However, I think that in this type of molecule, this type of an example, this hyphenation really makes it clear where those functional groups are going to be located. 2 has the double bond. 1 has the alcohol group, but there's other things on this too, right? So this is carbon 3 and this is carbon 4. This is a chloro group, that's a chloro group, and then here at spot 2, I've got this L-shaped group, and I hope that you remember that that L-shaped group is called isopropyl. So C comes before the I. All right, so this is going to be 2 chlorines, so this is a dichloro, and that happens at spot 3, and it also happens at spot 4. So 3,4-dichloro. At spot number 2, that is where the isopropyl group is going to be found. So 3,4-dichloro hyphen 2 hyphen isopropyl butene 1-all, and we're not finished yet. Why? You just told me that this was an E, didn't you? And that E location can be written in the very front. Now, there's only one double bond here, so it will be understood that at the double bond location, it will be the E position. However, if you are uncertain, it's not going to kill you, it's not going to hurt you, it's just going to take 1 or 2 seconds for you to do it. The double bond location happens at spot 2, so I can easily put a 2 out in front, just to clear up any confusion. 2E34-dichloro, 2-isopropyl, butane, 2-butane, 1-all. That is going to be the IUPAC name for that compound. Yeah, no one said this is going to be pretty. And again, it's a build-up process. If you've not noticed that yet, well, here you go. I mean, we've wrapped everything up in Module 4 that we've been talking about. We went back and wrapped things up in Module 3 that we've been talking about. All of it's kind of coming together. And that's what will continue to happen throughout the class. You can't forget about any of that older stuff because it's going to come back to haunt you, people. It's going to do it. Okay, so now let's do another example. All right, that was a very complicated example, by the way, for naming. We haven't really made it that far yet, so if you struggled with that, that's okay. I've not asked you to master that yet. So let's do another example for E and Z. So on the left-hand carbon, let's do a CH2 group, and then maybe like a OH group that happens here. And I've kind of wrote it in order of how it's connected. Here, let's do a C triple bond CH. Over here on the right-hand side, let's do a CH double bond CH2. And then down at the bottom, let's do a CH2CH3. Okay, we're only going to determine if this is E or if this is Z. That's all that we're going to do here. Okay, so to the left-hand side, that left-hand carbon, I'm going to compare that carbon to that carbon. Ding, tie. I move on to the next. All right, I move on to the next. I get a carbon here and I get an oxygen there. Which one beats out? Oxygen. Why? It has a higher atomic number. All right, so this is a higher priority group. I'll circle that. Right-hand side. Notice I didn't care about the triple bond yet. We were comparing the atom atomic numbers. That's all that we were doing. Oxygen beat it out. All right, to the right-hand side, I compare that carbon to that carbon. Ding! Tie. All right, I move on to the next. I compare this carbon to that carbon. Ding! Tie. Oh, now what do we do? Well, this double bond is there, so therefore we're going to count this a second time. So there is another carbon kind of there, and then here at the bottom we run out of choices. If we run out of choices, by default going to hydrogen. So which one beats it out? Another carbon or a hydrogen? And another carbon will beat it out. And that's why this has a higher priority over those two groups. So the two priority groups are on the same side, and because of that, Z groups are on Z same side. We label that with a Z notation. So there's you another example of how to compare these two. All right, let's do another. Carbon, double bond carbon, and we do an H, and we do a D. A what? A CH3, or sorry, CH, CH3, CH3, and then here, CH, double bond, CH2. Okay, so let's talk about a few things here. It's the first time I've did this to you. Again, it's all learning. You paid tuition dollars for a reason, didn't you? What does the D stand for? Hopefully not your grade. You don't want to see that on your final grade. So what does the D stand for? Well, in general chemistry, you probably talked about isotopes. And with those isotopes, they love to talk about hydrogen isotopes. I mean, it seems like that's the only thing they want to talk about. However, a lot of things have isotopes. It's where nuclear chemistry comes from. So isotopes, hydrogen has 3 versions of an isotope, and hydrogen has just normal old hydrogen. Ideal body weight right there. But hydrogen also has something called deuterium. Deuterium is a heavy hydrogen. And when we say heavy, it has an extra neutron. That is what we abbreviate with D in organic chemistry. So it's hydrogen, but there is a extra neutron in play. So there's something extra that's there. Well, hydrogen also has something called tritium, and tritium is, of course, H3. It has even a higher neutron number. So it's fatter. That's basically what that means. We have normal hydrogen, then we just have a little bit of lazy hydrogen that's slightly overweight, and then we have a big, huge Mama June tritium hydrogen that comes around. Okay, so, of course, now she's not that way. She went hot to not, didn't she? Okay, so, or not to hot. Maybe that's what the title is. Who knows? But those are the 3 isotopes. So if I look at the left-handed carbon, I'm going to compare the hydrogen to heavy hydrogen. So they are different. And now I need to figure out, well, atomic number is a tie here. But this has a higher neutron number. So I'm going to give this a higher priority group over just the regular hydrogen that will come around. Then on the right-hand side, I do that carbon and that carbon, ding, tie. I then move on to the next. I do a carbon and another carbon, ding, tie. And then I move on to the next. Well, in the longest chain, I kind of run out of room here, right? I can't really backtrack and go back up. The game doesn't allow me to do that. Once I pass it, I really just do have to go with it. And those 2 carbons were a tie, so that's why I just went right-handed with it. So I get a carbon, and now I've ran out of choices. This defaults back to hydrogen. And then down here at the bottom, well, that has a double bond on it, so I can really count that carbon again for a second time. And because of that, that has a higher group number than the one up above. These 2 groups are on Z same side, so therefore this is the Z nomenclature. Okay, now let's take a look at an example. Here we go. So this question says, assign the relative priorities to each set of substituents. What they want you to do is they're going to give you, for A, 4 choices. And they're going to say which one of these has the highest priority, which one would come next, which one would come third, and which one would come fourth. All right, so this is a pretty easy question. This is how we answer it. We look at those choices that are there on the screen, and we say, which has the highest atomic number? That's all we got to do. If we have the periodic table in front of us, we can answer these questions without a problem. So iodine has the highest atomic number, so it gets the highest priority. Then bromine has the next highest atomic number. That one would get the next highest priority. All right, then we have an O and a C. Out of these 2 choices, oxygen has a higher atomic number, so therefore that's ranked as group 3. And then that carbon, of course, will finish out the end with number 4. All right, for B, we do the same thing. Here we have a carbon, and then we have an O, and then we have a carbon, and then we have a carbon. Notice that line that's right there? That line represents the line that's connected to the carbon double bond. That's what we're looking at. That's why I'm starting here in each single case. Well, oxygen beats out all of them. And it doesn't matter that that OH is in this. Okay, that has nothing to do with it. We go in order and we look at one at a time. So this is going to be ranked to number 1. That was thrown in as a trick. All right, now all of these others are a tie. Carbon, then carbon, then carbon. So I move on to the next one. All right, so here my next one is a carbon. And then here I've got a chlorine. And then here I have another carbon. All right, well, carbon, chlorine, carbon. Chlorine beats them out. So for that reason, this is going to be ranked as number 2. Then I need to go to the next atom. The next atom here is going to be the oxygen, and the next atom here, that's a double bond, so that's going to understood to be another carbon. So I'm going to double up on it. Now I'm comparing the oxygen to the carbon. The oxygen has a higher number than that carbon does, so this is going to be ranked as number 3, and that means this is going to be ranked as number 4. So that's how we answer those types of questions. That's how we determine which one has a higher priority than the next. So just a couple of more practice problems that we did there. Hopefully you feel a little bit more comfortable with ranking atomic numbers in these more complicated groups that might show up on an organic molecule. And then in the next video, we'll continue this discussion. We'll do more examples because I know that you're going to ask for them. So we'll do more examples. That way you'll feel more comfortable with these types of questions that are coming around.